turned it in, but if you turn it up to 2:45 tomorrow, it will be considered within 1 day late, and you'll lose 10%, and up to 48 hours, so 2:45 on that'd be on Friday. That'd be up to 2 days late. You lose 20%. After that, you can't turn it in.
Are you going to be posting some sort of answer key or something along those lines after that late period?
So I'm not planning to do that. So hopefully when the homeworks are graded, the answer should be apparent. If there's something a lot of people had trouble with, I might kind of explain it in class or something.
Okay, I was just curious for the quiz on Monday, if there was any sort of back before that.
So yeah, so as I mentioned before, the homeworks and the quizzes are not aligned up so perfectly. So we aren't going to. It's possible we'll get stuff done, and if it's all graded by Monday, and I see something, then in class on Monday I could go over something that was a big issue with everyone, and that would be before the quiz. But it's I'm not sure if we'll get something turned around in that schedule, right? If there's something there's big confusion, I'll try and post something about it. Otherwise, it'll generally you hopefully you can decipher it from the comments on Unit Campus. Yeah. So okay, so if you turn in late, you can still do that, and remember that you can also there will be 5 homeworks and 4 quizzes, and your grade is going to drop the lowest one. So the third homework on this assignment, I think was a little slightly more difficult than I intended. Hopefully this was good, and it really forced you to think and understand what was going on, because you didn't just have to, by rote apply some equations, but really figure out what was going on. And it's a little bit more difficult than I intended, but hopefully it enhanced your understanding of that process. So I hopefully the future homeworks won't, sometimes I'll unintentionally make it a little bit harder or a little bit easier than possible. I don't intend it to be kind of quite all the nuances and trickiness that ended up in that question because of some ways I phrased things. So other thing coming up, so let's see, by a week from now, I will post homework 2, which will mainly be about the conversion section we're talking on now, and then some basics of linear algebra that we'll start covering so next week. And then quiz 1 is on next week, Monday. It will cover topics up through the lecture today. And you are allowed to bring in 1 sheet of paper with notes on one side of it. You can write anything you want on there. You can work together to write notes if you want to. I think kind of writing out just yourself what you think are the most important things is a useful way to study for these. And the point of the quizzes is not because I want to make your life stressful, but it turns out that if you're forced to kind of think about these things for an upcoming quiz, you'll ultimately learn and retain the material better. So that's why we're having these quizzes. Okay, the quizzes are not meant to be hard. They're meant to be things. Think of like the homeworks, or if you look in the book, it's got some other similar questions to the homework questions. It'll be like those, but easier. It's such that if you really just knew it, you could write down the answers in like 5 minutes. Okay, it might take a bunch of you longer than that, but if you know it, I'm guessing a few people will finish in like 5 minutes or so. Go ahead.
Speaking of those extra textbook questions, would it be possible that we could get a solution key to those so we can do them and check our work?
So I've not made a solution key to them. I bet if you ask the TAs, they they can help you with those. I haven't decided whether, for the book, whether I'm going to actually post a solution key online or not yet. It's kind of an issue with textbook. If I post it online, then anyone else in the world who's the textbook will have solutions to that. I haven't quite decided what to do about that yet. I'm leaning towards not so far. But I bet you can check your answers with the TAs, and that would be a great way to study. And the questions in the book are actually more similar to the homework difficulty of questions. Think like those, but like a sub piece of that, right? So question 3, you basically had to combine together like 4 or 5 different concepts to answer that question. And the question on the quiz, there might be 2 or 3 questions on the quiz, and it would be like just one of those concepts, right? So it shouldn't be as difficult or as broad. There won't be anything in Python on there. It'll just be kind of making sure you're kind of paying attention and in the class. And there's no calculators or phones or computers open. I just don't have to deal with the possibility of covert ways of communicating between people in the class. So, but I think the one sheet you should be able to write everything down that you could possibly. And then I think the last on the final, I think I'll allow you to have 4 2 sheets both sides. So if you do this kind of in the right way, you can kind of copy all your questions now, all your notes now onto use for the final. Okay. So any other kind of administrative questions? I heard that the office hours this week were really crowded, and that they were empty up until this week, almost. And I know this is generally how it goes with homeworks. Do you think we should try and skew the office hours, or will you maybe try and think of using them throughout the semester instead of just right before the homework study? Any thoughts on that?
The latter.
So you'd rather keep them roughly how they are, and then you guys just plan ahead a little bit better? Yeah? So, okay. So I mean, I'm asking for feedback, and then we can, if you'd like me to change it, we can discuss with the TAs and work out a schedule that way. But this way, there's always something there, whether there's a quiz or a homework coming up. I think this ultimately works out better. Okay, great. So we are talking about concentration bounds. And on Monday, we started by discussing the central limit theorem. And this was, you have these IID, so random variables, x1, x2, up to xn. They're all drawn from the same distribution f, okay? And we're interested in looking at this x bar, which is the average of these random variables, and want to know about the distribution of x bar. What happens when we concentrate these? Okay, and so for this, the most general form of this, for this to work, I need to know that the expected value of each of these is mu, and the variance of each of these is variance of each of these is bounded. And so basically, what I know is about this is like 3 things. One is that the expected value of x bar is also equal to mu. The variance of x bar is equal to the variance of xi divided by n, and that the PDF of x bar, it somehow converges to some sort of normal distribution. Okay, so it's converging to this normal distribution. As it's converging, the variance is shrinking. There's ways you can state this so that you think of the normal distribution times n, and then it's converging to where the variance is times n, so it's converging to a fixed quantity. But this convergence is like a little bit mysterious and hard to state, and it depends a lot about properties of f, which we would like not to have to state. Okay, but the expectation is the same, and the variance is shrinking with the factor of n. And this tells us about what happens to the quantity that when you are averaging a bunch of random variables instead of just looking at that one random variable. And the idea is that it stays basically around the same spot, but it becomes more and more concentrated, right? I start from a distribution, maybe this is f of x that I'm drawing from, and then the concentrated, that was gone. That was kind of cool, not what I intended. And then the concentrated version, this one is f of x bar. So they have the same mean, but the variance is shrunk. It's much more likely to be the case. Okay, and then we talked about these pack bounds. Okay, so it's kind of easy to understand, I think, hopefully, that the expected value is basically staying in place, and the variance is shrinking. But what we really typically care about is kind of how this corresponds, like how this affects some tail quantity here, right? So let's say I'm willing to go out an epsilon distance from the mean, and I want to say it's bad if it falls in these tails here, right? So if I integrate these tails and this integral, the sum of these parts outside of some acceptable range this is kind of a bad result. So I don't really care about exactly how much it looks like the normal distribution. I really just care about how far away or how unlikely I'm to see some actual value when I actually realize this random variable that's outside some error tolerance. Okay, and this gives me to the form of so this pack bound, and this is basically looks like the probability that x bar, that the distance from the expected value of x bar. Okay, and this expected value is the same as the expected value of x, it's mu, right? So that the probability that this is greater than epsilon is less than delta. Okay, so this is, again, the error tolerance, and this is the probability of failure. I'm outside my error tolerance. Okay, and so there are other ways you could try and state how well I'm doing, but this is typically the form that we're looking for. And it's not necessarily just a distance in here, but it's something like I have some error tolerance, the probability that the value I get is too far from what I would expect in some way, and I want to bound that probability. I have one parameter for being high error tolerance, being what does too far mean, and what is the probability bound? Yeah.
So what is the DAC? Does that work?
So probably approximately correct.
Okay.
So I'm probably, with probability 1 minus delta, approximately with an error tolerance epsilon, have the correct expected value. All right? So there's the probably, approximately, it's confusing terminology, but there are these two error terms that I need to worry about, the probably part and the approximate part. All right, so how many of you have seen like an approximation algorithm before? Have you taken any class where you've seen even an approximation algorithm, where you're constructing, where Typically, with the sort of kind of a typical problem you see is like trying to do sorting. You start with an unordered set of points of values, and the algorithm only is successful when they're exactly sorted, right? And so this is the kind of common classical version where people think of in computer science. In the algorithms we'll be talking about in kind of more in data science, you typically may not get to the exact answer, right? I may exactly want to recover this mean, and this is some estimate I get from some data, but it won't be exactly on the mean. And I'm willing to stop before it gets exactly there. Now, there are versions of it where I don't have a probabilistic version. I just said, I know I can run this so many steps, and at that point, it will guarantee to be close. And that's guaranteed without any probability. In this case, I've got some error, so it's an approximation, and some probability of failure. So I'm somehow having to combine both of these concepts together. It's you know, this is can be a little confusing. Yeah.
So gradient descent being approximation?
So yes, yeah. So great. So gradient descent, we will talk about gradient descent for like a week or so in this class. And that's an example of an approximation algorithm. You're trying to find the minimum of a function, and you keep taking steps. And you might accidentally kind of get to the true minimum, but probably you just keep getting closer and closer and taking smaller and smaller steps, right? So we'll spend some time on that. We'll see several approximation algorithms in this class over the semester. Some of them will be probabilistic approximation algorithms. Like we'll look at something called stochastic gradient descent, which is a randomized version of gradient descent, which is what is used in almost all of machine learning as the kind of the core kind of thing they use to solve the model, and it is a probabilistic algorithm. So it's a gradient descent. It keeps getting closer to the answer the more you run it, but in probability. So we'll have to kind of combine these together. Yeah.
Is the goal of this to recover the population mean then? Like, just given some data we've sampled, we're trying to recover what the true mean is?
Yeah. So everything we're talking about now, we're just talking about the true mean from the population mean, essentially. This is what is the probability that if I realize this random variable, which is x bar, which is the population mean, the sample mean, that is within an error tolerance of the true mean. Okay, so I've got some probability distribution here. All right, so this will be f of x bar. Right, so this looks like a normal. Maybe this is accumulated from some central limit theorem, and maybe f of x was actually something much wider. Right, but this is f of x bar now. And every time, and I can say, well, there's some true mean. This is the true mean of f of x bar. Okay, and every time I run an algorithm or I collect some data, I'm going to get some data point. Right? Sometimes I'm going to get this data point, sometimes this one, occasionally this one here. Right? And I want to know what is the probability that when I run this algorithm or I collect this data and I set some tolerance epsilon, what's the probability that the data point falls outside of this range? If I say if it's close enough, I'm okay. You know, I'm not going to sweat it that it's not the exact right mean, but it's close enough. But there's some probability I get outside. I need to have both of these terms to properly describe what's going on.
Does f have to be a random distribution, or can f just be anything?
So x bar is a random variable, and in this case, we'll usually be talking about continuous random variables. And so then, if it's a random variable, then I can discuss it with respect to the probability it induces, and that is described by a PDF. So that means this will be a probability density function, and it will integrate to one.
It doesn't have to be normal distribution.
It doesn't have to be normal. Yeah, it doesn't have to be normal distribution. Now, if this is x bar and it's the average of random variables, I know it will look like a normal distribution. So it's not wrong to draw something that looks like a normal distribution. Again, my artwork on the board is converging towards a normal distribution. It's not there either. So
The F, like the right below central limit there, like that you're drawing from that probability
this
distribution.
one does not need. This
Right,
does
right.
not need to be.
That's
This
what I
could
thought.
be anything with bounded variance, as long as this is bounded. And so there, as I mentioned, there are other ways you can kind of formalize this part of the theorem, but we only typically care about this one. This is what we need usually to get a bound on how well the analysis of what's working, how many samples we need, or how fast the algorithm is running. We typically need something like this, right? With probability bounded by this quantity, the algorithm does not run longer than this amount of runtime. Right? This is the expected, but it doesn't run too much longer than this. And that's just the area under this part of the curve. Okay, so let me give some ways that we can actually go about trying to quantify this by telling you a little bit about F, and I'm going to tell you it's kind of 3 simple ways of thinking about it. The first one is I just know F is positive, and I know the expected value. The second, I will know the expected value and the variance. And the third, I will know the expected value and some absolute bound that it's on the left side and the right side, that it has to fall within. Okay, and these will give us tighter and tighter ways to kind of get bounds that look like these path bounds. Okay, and so the first one is called so the Markov Inequality. Okay, and so this says you have a random variable x, and I know 2 things. I know the expected value of x is some quantity mu. I have to know this to write down the bound, and I know that x will be greater than 0. Right, so this is basically the probability that x is less than 0 equals 0. Right, so it's never it's never less than 0. Okay, and I could know more about the random variable, but I only need to know these two things. And now I can say that for any alpha greater than 0, I say the probability that x is greater than alpha is less than the expected value of x divided by alpha. Okay, so this is kind of a weaker form of this. We'll get to forms that look more like this one here. This is only saying the value of my random variable can, like the runtime of an algorithm, right, cannot get too big. And I bound this based on the expected value of x and this term, right? If I set, as I change alpha, this value, then this one changes. This is on both sides here. Okay, so let me, okay, and so basically, this guy, so in some sense, I could say that epsilon equals x minus alpha, and delta equals the expected value over alpha, right? So I can put it into these epsilon and delta form here, you know, in case that's not that's not clear. But this one's only one-sided. This is two-sided. There's some little bit of weakness here, but okay. So let me try and explain this, and then we'll go through some simple examples of how to use it, and then we'll see the other ones. This one I can actually, I think, very informally but I think hopefully convincingly explain to you why this has to be true. You can think of, so I have some plate, okay? And so if you ever seen like a waiter or waitress or you've been a waiter or waitress in a restaurant, and you're balancing kind of a tray of like glasses or plates on your hand, right? You've got some point here, right? And this you want where your hand is under here. You want the center of mass of the plate to be under your hand. If it's outside of your hand, it's going to tip over. Okay, so I can think of having a probability distribution on here. But so it can be any probability distribution, but I know that the expected value of this probability distribution is this is the expected value of x is right here. Okay, and so the expected value is the center of mass. These are effective. These are equivalent. Okay, and so the question is, I know, let's say now that the plate or the tray has a 0 point here, but it actually, and the tray itself has 0 weight to it, but it extends really far out here. Okay, so I want to say, how far can I put something out here? And alpha, right, I want to put a delta quantity. I want to put a delta quantity out really far so that the center of mass stays in the same spot. Okay? So if I want to do this, what I would do is I would chop off some delta quantity here and shift this out to this area. Delta, and so so this area is going to be basically this alpha, right? Where I put all this mass, and it can be further out. I'm not saying it can't be further out, but I want to put it there, and then but I can shift this stuff over in this direction, right? So I can take this, but I need it. It has to be positive. It has to stay in the tray. So I'm going to stack it completely up here. Right, so this has probability 1 minus delta. This is 1 minus delta fraction of the weight. This is 90% of the weight is here, and 10% is out here. If I keep the expected value in the same spot here, how far can I push alpha fraction? Or how far can I push delta fraction of the weight? Okay? And so if I write this down, I know the expected value is fixed. I know the expected value is going to be equal to 0, this location, times probability that x is equal to 0. And this I know is 1 minus delta, plus this distance alpha here, times the probability of x equals alpha. And I know this quantity is delta here. Okay, so this is equal to 0, this term, plus alpha times delta. Okay, and so I can say that then then I can solve for alpha. I can solve for delta, which is that means delta is going to be equal to the expected value of x over alpha, which is exactly here. So the probability that the mass is greater than alpha is at this point or further is at most delta, which is expected value of x over alpha. Right? So if I'm pushing, if I have a probability distribution and I know the expected value is here, well, it can't be less than 0, and this has to average out. Right? So if I'm just knowing the expected value, I know there can't be too much mass out here. Okay, I also want to draw, say, 2 pictures here. Okay, so let's draw 0, 1, up to 5, 6. Okay, and I'm going to draw two probability distributions. Make this a little more. Okay, so the first one is going to look like this, and the second one probability distribution will look something like this. Okay? So these two will have very different averages. This is the expected value of x. Let's call this f of x. And this one f of y. F of y, the expected value will be here. Okay? And so now I want to know the probability. I can look at, say, the probability that x is greater than 5, and the probability that y is greater than 5. Okay, so both of them have these probabilities that I can write down as the area under the curve here. Okay, and so I think those areas are actually pretty similar to each other, roughly based on the board. Okay, but I'm going to get a much better bound for y because I know the expected value is smaller. Y is closer to the worst case for this bound, and x is closer to kind of an average case of this distribution.
Do you just put the expected value wherever?
You have to put it so that it's like the center of mass of the distribution. If I were to integrate over this,
I mean, just visually seeing it, I thought expected value of y would be like somewhere within the square-ish area.
Oh, in this area?
Yeah.
So well, there's, say, 10% of the mass is pulling it out over here. Right, so it's going to be weighted by 90% over here and 10% out here. So think of it as moving about 10% in that direction.
Oh, I see.
Right, it's roughly how to think about it, where this one is kind of in the middle. Maybe it should be a little bit further to the right. I didn't draw it perfectly. But this one is more centered in the middle. This one is kind of this pulled out here. So if I were balancing this, right, this was the amount of weight. I was stacking kind of clay or something on a lightweight tray. I could actually balance it on my finger right here, roughly, and similar for the black distribution for x would be about here. So that's the way I think of the expected value. Okay, and so if I know here, let's say this value is equal to 1, and let's make this a little bit simpler. Let's say this value is equal to 3. Okay, then I could say that this is going to be less than the expected value of 3 divided by 5. It's 3/5, and this is less than 1 divided by 5. It's 1/5. Right, so 0.6, 0.2. Okay, maybe it was 10% of the mass of both of the distributions was to the right of 5, but the green one I happen to get actually a much better bound. I'd say it's at most. I know it's at most 2% and most 20%. With this one, I know it's at most 60% because if this was actually part of it all the way over here and part of it kind of exactly at 5, I could balance 60% of it out over here. if I did it just right, where the green one is close to the optimal height. And maybe this should be closer to the 0.5. If this was 0.5, then it would be exactly 10%. And maybe that's exactly the extreme position of what it would be.
So I just want to be sure. So like the area under the curve represents the probability. Is that correct?
Yeah.
And we're saying that 10% for both f of x and f of y have probability past 5, or sorry, greater than 5. So each one has probability greater than 5. But the probability, what we're saying here is that we're saying not the probability of what's past 5, but we're saying the probability of, I'm trying to think, I'm a little confused, like what we're trying to say.
Yeah, so like typically you are not given access to know the full distributions. They're messy, they're hard to describe, but maybe you know the expected value. You know that analytically, or maybe you're cheating and using the sample estimate as the expected value, something like that, and you can calculate that somehow. So, you know, maybe just by moving your hand until it's not falling over, right? And use that expected value, and then you say, well, I just want to know, well, the edge of the tray is at a distance 5, right? How much of the probability could be out there, right? So I've got a more concrete example in the book, which is a little hard to draw, where I have like 10 balls, and I want to move one of the balls, which is worth 10% of the mass, as far as I can in one direction, and stack all the other ones at 0, right? So how far can you move it without keeping your hand at the center of mass without it tipping over, right? But you could be these continuous quantities as well. So in these cases, you don't know the true distributions. You just are trying to understand the probability that they're very extreme.
So it's all we're given is just based on the mean.
Yeah, we're just given the expected value and some notion that it has to be positive. Well, a lot of quantities, like, I'll give you an example with the amount of coffee someone drinks. It can't be negative, hopefully. So,
if there was negative numbers, would it be possible to just shift them over until your lowest number is 0?
Yes, yeah. So you can. I wrote down the notes a way where you can introduce a different lower bound, and then basically say the probability that this is x is greater than alpha minus this other lower bound is less than or equal to the expected value of alpha minus that quantity. It's you can throw some algebra in there and then you can extend it. Yeah, this is usually how you see it, but you can apply it these other ways. So sometimes you get like these word problems where you need to apply this transformation. Yep. All right, so let me give a different, less pictorial, more kind of straightforward example. Okay, so let's say, okay, the faculty in the computer science department, okay, so drink, so C liters of coffee each week. Okay, C is a random variable. Okay, and and let's say the expected value of C is equal to 20. Okay, you know that the SOC faculty drink 20, on average, drink 20 liters of coffee every week, and you know this quantity has to be positive, right? It's not negative. Your job is to keep the coffee for the faculty stocked at the beginning of the week so they won't run out. Okay, so I want to set the amount of coffee I have in stock so to make sure it doesn't run out until next week high enough so the probability they don't drink more than that is low. Right? So I want to write down so the probability that the coffee consumed is greater than 50 liters. Okay. All I know is the expected value. I've been tracking this data over the last 50 weeks. On average, they drink 20. I'm saying this is the expected value. Okay? And so I know that this is going to be less than the, so for 50, it's less than the expected value of C divided by 50. That's 20 over 50 equals 0.4. So with 40% of the time, no more than 40% of the time will we drink more than 50 liters. And this may not be a satisfactory balance. 40% of the time, it might be 40% of the time we actually run out of coffee if I only have 50 a week. Because on weeks there are deadlines, we drink lots and lots of coffee. And other weeks, we don't drink as much. Right? So maybe it's like this distribution, right, where it's very spread out, where 40% is here and 60% is over here. And in that case, I'd want to stock more. This would not be sufficient. All right, whereas if I use this bound and I set this to be like, set this to be 100, it would only go down to 20%. Okay, so this bound is, you know, it's okay. Sometimes it's the only thing you have, but it's not that great, right? I'm going to now introduce another bound that, and then we'll come back to this example, and we'll see how to get a much tighter estimate of this. Okay, so the next bound is called the, the Chebyshev inequality. Okay, and so this has a random variable x, and we know the expected value of the random variable is mu, and the variance of x equals sigma star. Okay, so now I don't necessarily need to know that x is positive here. It could be I know that, but I also have this additional bound on the variance. Okay, this green distribution had pretty high variance here. So if I know that it's some bound on the variance, I'm less likely to get something like that. Okay, and so the result is I can write that the probability that probably the difference between the random variable and the expected value is greater, equal than epsilon, is less than or equal to variance of x divided by epsilon squared. Okay, so before, the expected value was kind of serving like a distance from some kind of limit. The expected value in 0 was kind of giving me a quantity, and I know that it didn't go too far to the left, and that's all I was using. And if I just have that, it's going down at a rate of 1 over alpha from this quantity. Now I can use the variance. The variance is a squared quantity, and it turns out it can be divided by, let's use, yeah, we can use, what do I say in the notes? Yeah, so let's use epsilon. It can go down by this squared quantity, epsilon squared. Okay, and so again, this is the delta probability of fit. Okay, it turns out the argument of why this is true is going to work the same way as kind of this argument with the Markov inequality. The actual formal proof follows some argument that looks like this with a bit more care. But you stick in, if you remember that the definition of the variance, you can write it as an expected value, and you kind of stick that in here, and then this side talks about the probability of the variance having some property like this. So it's an extension of this proof, but I won't try and go through that. But this gives me what ends up being a much tighter bound here. I can get a much better bound of what's going on here. Okay, so if I go back to here and now I add in some information, let's say now that I know that the variance of C is going to be equal to 9. Okay, so now I know not only have I kept track of the total amount of coffee and divided by number of weeks, I've also looked at I've kept track of the variance of the coffee as well. Okay, the variance of the coffee consumed every week, and let's say it's this variance is 9. 9, that's liters squared. Okay, so now I can write. I'm going to lose something. Okay. All right. Now I can write down that the probability that the coffee is greater or equal to 50, this is going to be less than equal to that the probability that the coffee minus the expected value is going to be greater or equal to 30. Okay, so kind of this is important to see what I've done here. I've translated into the form of the theorem. I want it to look like the difference from the expected value. And I know that if it's greater than 50, that means that the difference from the expected value, which was 20, was at least 30. Okay. Now this could also be true if it was less than less than minus 10, right? People brought their own coffee into the coffee machine every week, equivalent of 10 liters worth, right? So it's this could also be true if the amount of coffee was less than minus 10. Right? Remember this quantity was 20 here. But I'm just upper bounding it, right? I'm just getting an upper bound here, right? So the probability it's greater than 50 is less than the probability it's either less than minus 10 or greater than 50. Okay? So I've translated here, and I've this is an inequality. Okay, now I can apply the theorem, and this is the variance of C divided by 30 squared, okay, which is equal to 9 divided by 900, which is equal to 0.01. Okay? Good, so now, if I know the variance here, now I can say the probability that the professor has drank more than 50 liters of coffee is less than 1 out of 100 times. Okay, so by adding this information, I can get a much tighter bound. Yeah.
So we're just saying the probability that it's outside of those ranges is what we're talking about.
Right. So I'm only bounding that. So I know that if I know this and I stock 50 liters of coffee, that's to last the week. Has to last the whole week. I know that at most 1 out of 100 times, roughly at most 1 every 2 years, are they actually going to want to consume that much coffee? And there's going to be an emergency coffee request at the end of the week or something. Okay. Now it's possible the number is even lower than this. This is just an upper bound. I made an approximation here, right? Maybe sometimes people bring in coffee and there's some weird negative stuff, or I'd set the, maybe this makes sense where, this quantity was 40 and this quantity was 70, so I've shifted it forward, so then less than 10 liters of coffee is also a reasonable thing. And so, but I've lost that in this inequality here, right? And this is, there might be other things I know here that I've lost in this inequality. So it's not a no for sure. The same way both of these inequalities are true, right? These are both bounding the probability the coffee is greater than 50. They're both starting at the same spot. This one says less than 40% of the time. This one's less than 1% of the time. They can both be true.
What did you just find epsilon was 30 again?
Because I wanted to know the probability that the amount of coffee was greater than 50, and the expected value is 20. Right? So if you get word columns like this, great idea to draw a picture. Expected value is 20. I'm interested. This was 0. This is 50. I want to know the probability it's out here. So I want, so then the difference, I want to set epsilon to what looks like this. And this difference between 20, this is, the difference between 50 and 20, this would have to be 30. What makes sense? Okay, so this can be a much stronger bound if you have this information. And I'm basically, if you think of this variance is basically giving me a quantity. That means the standard deviation is going to be equal to 3. And that's kind of going to mean if I squint at it, it will probably look like a Gaussian distribution where this standard deviation is 3. Right? So probably saying it looks like this and it's unlikely to be out here. It doesn't have to be a Gaussian. It could be any, I don't know what the distribution is. But if the variance is 3, I would have to be really extreme to have some part out here and still have this expected value. This is kind of intuitively what's going on. So I'm incorporating this extra information. It's not necessarily Gaussian, but it's, it would have to be like this green distribution where it's very skewed, but it's still maintain this expected value. How much can I squeeze outside this range here? And that's what the Chebyshev inequality is capturing. Yeah.
Are you getting, I know we're just saying we have 9, right? But are we just using collecting data for a year and then doing the variance of that sample, or how do you get 9?
Right, so in classical statistics, you make some assumption about your distribution. This goes into your prior in some sense. You just assume this about the data. Maybe you've made sample estimates and you use that to inform your prior, but you're not really going through that kind of converting from the sample estimates to real estimates here. There's something else lost there. We'll use this inside of some algorithms. So the main use case will be some randomized algorithms, and we'll be able to, based on how long we let it run, we'll be able to control the variance. We'll be able to prove the variance is bounded, and we'll prove the expected value matches what it's supposed to match, without actually knowing what the actual data is. But we'll be able to state bounds like this. So it kind of depends on the situation. There's an oracle who tells you these things, right? So in the case of algorithms, which is mainly when we'll be using it, you can know these things formally based on how the algorithm is constructed. I think they're useful to think about actual sensing and analyzing actual data as well. That's more intuitive and simple to say at this stage. But you're right. How do we actually know these things? Okay, great. So So our goal was to understand the central limit theorem, though, right? We haven't done that yet. I've just talked about random variables and bounding these random variables. I haven't talked about what happens if I'm taking the averages here. I haven't explained that yet. It turns out the Markov inequality doesn't give you too much and doesn't give you a lot of concentration results. But starting with the Chebyshev, you can get some bounds. So you see that these improve as you increase n. Okay. Okay, so the important thing to know, what we want to analyze, we want to have these x1, xn, iid random variables, and what we want to look at x bar 1 over n xi, and if we know the variance of each xi is sigma squared, then if you recall from probability when we were doing the review there, we know that the variance of xi of x bar is going to be sigma squared over n. Okay, so now we can write a new theorem. So let's say we have n iid random variables, x1 through xn, and we know that the expected value of xi is mu, and the variance of xi equals sigma squared. Okay, we have these bounds. Then we can state that the probability that x bar deviates from the expected value of x bar, right? So I can write the pack bound here. If this is the probability it's greater or equal than epsilon, is less than or equal to delta. Okay, good. Is less or equal to some term which is equal to delta, and that term. Okay, let's look at the Markov inequality. The Chebyshev inequality for x. That was variance of x divided by epsilon squared. But now I want to look at x bar. Well, x bar is a random variable, right?
Sigma squared over epsilon squared.
Okay. Almost. This would, yeah, this is also true. So it's not incorrect, assuming n is positive. But importantly, sigma squared over epsilon squared times n. Okay? X bar, okay, x bar is a random variable. I know the expected value of x bar is equal to the expected value of xi. Right? So I can just, that's the same as before. And the variance of x bar is here. So I just plugged that in. That was sigma squared over n. Sigma squared was the variance of each of these individuals xi. But as I average together more of them, the probability I'm going outside my range goes down at a rate of 1 over n. Okay, so what does this mean? Here, just a simple thing. If I were to average, I would pre-process not for 1 week, but for 2 weeks. Right? So I said that they, effectively that would say that if I pre-processed and bought 100 liters of coffee, right, and said this has to last you 2 weeks, guys, all right, can you survive on 100 liters of coffee for 2 weeks? Then the probability goes down by, in this case, a factor 2. Okay, so it would go down by a factor 2 here, and so it would get to 0.005. And if I did it for 3 weeks, it'd go down by a factor of 3, so it'd be 0.003333.
Is this the saying that the more data that we look at, our assurance we kind of converge to like a lower range?
Yep, that's right. That's right. The more data you get, the more concentrated your estimate is of the mean. and any other quantities. I'm going to make Ben White crazy by going back and forth here. Okay. Okay, let me write up one more inequality, and then we'll compare that against the against the Chebyshev inequality with another example involving n. And you'll see how these things can like drop to be very small. Okay, so let me do this. Okay.
Does this inequality have a name?
Yep. So this is going to be called. It's complicated. There are multiple names which involve two different variations of this. I call it the Chernoff-Hofting inequality. Some people would call the version I present so a Zuma's inequality. Okay, but so the Chernoff-Hofting, and depending on your translation, these might have different spellings. Again, why that was a strangely complicated question. Okay, so might just call it the Hofting inequality, or I don't know. Okay, so this one is explicitly about, I've got n independent random variables, x1, x2, up to xn. Okay, they don't necessarily have to be IID. Okay, they can be IID, but they don't have to be from the same distribution. That makes more sense, but I'm just trying to write it slightly more general. I know, and I want to look at x bar. And I want to know that the expected value of x bar equals mu. And if I know their IID, then this is the same as each xi as well. And then, and I also know, so I know this quantity here. I also know that there's some range that each xi must lie in some range. So t minus b equals delta. Okay, so I know an upper and lower bound. Right, with Markov, I knew the lower bound was 0. Must lie in some range between values b and t. And the difference is, I just need the difference between these values. So I know that it's in some range. If you think of a uniform value between 2 and 7, then delta is 5. Okay. So now I can write okay, so now it's going to be a pack bound, and this is going to be delta again. This one I won't expect you to guess on this one. It'd be this. Okay, so what's happening here? So I'm getting a pack bound, and let's just interpret what's going on here. I want this quantity to be small, and the exponential of a negative, right, is going to be small if this e to the negative this quantity, if this is large. So think of kind of like a Gaussian distribution. It looks kind of like kind of like a, it tails off. So as this gets large, it's e to the minus, so it's 1 over e to this quantity. Right, so 1 over e to this quantity. So as n gets big, this drops off exponentially now. The probability of failure drops off exponentially. Okay, as my error tolerance gets big, it also drops off exponentially. Right, but it's counteracted by this delta square, this difference here. In a lot of cases, this might be 1 and you don't see it. Okay, but it kind of grows exponentially with this. Okay, so this is usually, if you can apply this bound, this usually is better than the Chebyshev inequality. And you don't really know which one will be better really until you try them. Like before, these both gave you estimates, and it happened that the Chebyshev inequality was better. But you can try both of these. Okay, so this is this other bound, and okay, so let's go through an example here. Okay, I'm going to roll a die, a fair die, n equals 120 times. Okay, and I want to estimate the how many times a 3 is returned. Okay, so t equals number of 3s. Okay, and so now I'm going to get or it's number of 3s divided by n. Okay, so let's call this t bar, right? So we're going to have t1, t2 up to tn, and each ti is going to be equal to 1 if a 3 and 0 otherwise. Okay, so now t bar is the number of 3s divided by n, right? Is the average. And then how about we say t is the number of 3s, and t bar equals t over n equals 1. Okay. Okay, so now the question I want to ask is right over here, the probability that t is greater than 40. Yeah, probably I get more than 40 rolls of a 3. Okay. So this is simple enough, you could probably calculate this explicitly, but we'll apply both of these bounds and see how well this works. Okay. Okay, so what do I know about this? I know the expected value of ti. It's a fair die, so this is equal to 1/6. Okay, I know that the variance of ti, I guess I know this is going to be equal to 5/36, it turns out. And delta is going to be equal to 1 because it's between 0 and 1. Right, so delta is 1 minus 0. All right, so this allows me to plug into these two inequalities. So by the Chernoff-Hofting inequality, this is less than or equal to, so I want to start by saying, okay, so this is I can bound this by doing this two-sided inequality. 1/6. Okay, so the expected value is 1/6, and t bar being greater than 40 would be would happen if it occurred 1/3 of the time. So 1/3 minus 1/6 is 1/6. Okay, so I've put it into this form, and this is kind of the form of the left-hand side of both Chernoff-Hofting and the Chebyshev inequality. Okay, and so by the Chernoff-Hofting, I can say this is going to be less than or equal to 2x of minus 2 1/6 squared times 120 divided by 1 squared. And this is equal to 2 minus 20 over 3, which is approximately equal to 0.00, so 26. Okay, so less than about 1/4 of 1% of the time is the upper bound. Then I'm going to actually get 43s if I roll this 120 times.
At least 43, right?
At least 43s. 40 or more, or
30, 41.
yeah, you can. I guess in my notes it says greater or equal than 40. There's some variations of whether it's less than or equal than. Not going to worry too much about them here. I'll mention there exist one-sided bounds for Chernoff-Hofting and for the Chebyshev inequality, which are slightly stronger. They basically, more or less, they'll drop the factor 2 here. And then you can maybe divide this by 2, roughly. So you can look up. There are a lot of more inequalities. These are just kind of the main ones here. Okay, so this was Chernoff-Hofting. If instead I do the so the Chebyshev inequality, I'm going to get instead so I'm going to get the let's see, so the variance, which is 5/36, divided by epsilon squared, which is 1/6 squared, times 120. Okay, and if I did the math right, this works out to be about 0.042. Okay, so this says maybe 4% of the time I could get I can get more than 43s. This bound in this case is worse. Okay, so this is not giving me as good of a bound. But there are other cases where you'll find actually because delta becomes very large in some settings, that the variance you have gives you a better bound, and this one actually works better, especially if n is not too large. But as n gets large, this one goes down exponentially. All right, so I have, okay, so we have about 5 minutes left. I can go through more examples or take questions. Yeah.
What did you times it by n for the denominator for Chebyshev? I mean, the formula over there doesn't have n.
Right, but this one does. I'm looking at the random variable for x bar. X bar is a random variable, and its variance is sigma squared divided by n.
Okay.
Right? So I know the variance. So when I have n things and I'm averaging them, instead I want to use this version of it instead. So this is the n random variable with n RB. Okay, you can directly plug this into here.
Oh, sorry. Where did the 3 come from in the SOSS 2 with the exponential -20 divided by 3?
Oh, there was some simplification going on that happened inside the steps of my notes, but this is 1/36. So I have actually 36 in the denominator and 240 in the numerator, and I think this is the simplest fraction, if that would work. Yeah.
Can you go over how you got that 1/6 for the top right? That one, yeah, that
Here.
1/6.
Yeah. Okay. So this quantity is 20. Expected value of t bar.
Okay. No, I got it. Yeah.
Right, is what? Sorry, is not 20. It's 1/6, right? And this corresponds with t bar is greater or equal than 1/3. Right. So in word problems and in situations, you'll need to be comfortable with somehow translating. This is probably kind of the way I've written it here, using x bar minus the expected value is usually the easiest form. Sometimes you'll see a version of this written where it's with respect to just the sum, not the average. And then you have another factor n that shows up in here, and then it shows up in the denominator or something like that. So there are different forms, but they're like algebraically just kind of dividing through by some quantity the same.
How did you have 1 as your delta?
Delta, yeah, okay, good. Good, so ti, each random variable, it's going to take in a value of 0 or 1. It's actually this discrete distribution. Right, so I've done with discrete distribution, but I can treat it like a continuous random variable. And so then it's the difference between them is 0 and 1. Actually, so the Chernoff inequality assumes these are 0, 1 random variables. And the Hofting kind of extended it to continuous random variables. And then this form is probably by so like a zoom out, although it's not quite like this. But. All right, so it's mechanically it's just like reading the word problem, whatever the situation, and then trying the different bounds and applying the algebra. Okay, so in your homework, and possibly something very simple on the quiz, I'll ask you about one of these. If I do it on the quiz, I'll try and spell everything out. But in the homework, I might say, here's a bunch of random data that I've drawn. I've assumed they're all IID, and here's the expected value that they should have had. What is the probability that the expected value of an actual realization is bigger than this quantity? Solve it with the Chernoff-Hofting inequality and the Chebyshev inequality, and report those answers. Right. So mechanically, you would walk through examples like this. Right. Later in the semester, we probably won't. We might walk through applying one of these on an example of an algorithm, but I'll kind of point to it. I'll say, look, we can bound the expected value, but we're interested in how far does the runtime or something, or the number of steps we take deviate, get too much more than the expected value. And either we can bound this or we can bound the variance. So you could apply a Chernoff-Hofting bound or a Chernoff inequality or a Chebyshev inequality, and you can bound the runtime in that way, right? So kind of intuitively, this gives us a way to give an upper bound on the runtime or the amount of data we need in with some probability, which we can set like 1% of the time. Great. Okay, so this will kind of be the main part of the probability kind of push of this course. We're going to start with linear algebra next week, and then we'll start thinking about data linear algebraically, and this kind of intuition and the modeling will show up throughout, but we probably won't kind of dive very deep into the probability after now.